You couldn't even hear me this whole time. Braden, Noel, Brooke, good to see you there. How is everyone doing? Now you should be able to hear me. I was in a meeting, and I mute myself in meetings sometimes. And so I had on the global mute. You should be able to hear me now. I can see the voice going up and down on the stream. That's what happens when Brian goes into a Zoom meeting and forgets to change things. So thank you, everybody right there. Imagine if I start a class like that. Oh, geez, the embarrassment. The embarrassment, the embarrassment. So with that, we are going to start up. I believe a good place to start would be going back and doing the project. Should we finish the project? If you're here yesterday, we can finish the whole project, which would be really great. Finish the whole entire project, no more project, do it in some videos, get it done, project over. My left arm is twitching. It's like, I'm dehydrated. Maybe that's what it is. Okay, let's go over here and let's get the project going. The speed on my mouse, it's either too slow or it's too fast. I can't get it perfect anymore. Okay, we're gonna open up the project. How are you doing, Noel? How you doing, Brayden? How you doing, Brooke? How is everybody? How is everybody? The project right here. Bring it over to the main screen. And let's start on the project. Right here. Advice on project. Stats 1. Project advice. Awesome, Braden. Good to hear that. So first bit of advice I have is watch yesterday's video. So please check out, if you're doing the project, check out yesterday's video. I'll link it in the chat right here. Well, you should see yesterday's video right now on stream, and we'll link it. So this is timestamped to everything you need, and pretty good. Still stressed about the finish. Nice job. So project part 1 is right here, linked. We'll even pin the comment for the moment. But that is yesterday's when I was wearing the Batman t-shirt. Today I wore Nightwing. Yesterday I wore Batman. So just changing up between heroes right there. I got these shirts for pretty cheap. $12. Wear a superhero t-shirt, it's cool. I'm good with that. So with that, check out yesterday's video where we go over the project and explain what's going on. And we're going to start up today where we left off and talk about the 2-sample T. Now you need to use your data from these data sets here. You need to take your random sample of 300 plus the last 2 digits of your UTID and use it. Brooke, good to see you there. Go watch part 1. Nice. And then check out part 2 right here where we're picking back off where part 1 stopped off. So I'm taking the random sample. You should have your random sample from yesterday. This is how we do the random sample, 300 plus the last 2 of our UTID. Make sure to save your random sample or else you'll get a different random sample each time. I'm just showing you how to do things. Yeah. And you can actually, if you have your random sample right here, you can start working on what we're doing here. And we are going to talk about the 1-sample T. So I'm going to give a little bit different of an overview today on the 1-sample T and give your understanding of it that you need for the test. So let's go here, Stat Tool 1, 1-sample T, theory overview. So the 1-sample T, we're mainly focusing in on the interval, and we can talk about the test. And we drew it out here yesterday. I'm looking to see if we have those notes from yesterday on the screen. I don't know if we do. We do have a sleepy bunny, though. Oh my God, look at Morty. He's so cute. He just passes out. He says, I'm tired, bunny. So, Morty's a good bunny. And Jolly's a good bunny. So the 1-sample T uses, for the interval, y bar plus or minus t star with n minus 1 degrees of freedom s over square root of n. Now, the thing is, when you go to the test, we have a saying, and it goes... Notation brother. You got to know what these things mean. A lot of people get stuck because they don't know how to find the t with star with n minus 1 degrees of freedom. When you use software, it'll often find it for you, but... if we had to do it by hand, you would use an applet or a table. So every T has with it what are called degrees of freedom. Degrees of freedom tell you the shape of the T, and for the 1-sample T, the degrees of freedom are n minus 1. That means, and say it in the chat for points, Mubot's here, if your sample size is 61, what would be your degrees of freedom? So if your sample size is 61 and you're doing a 1-sample T, what are the degrees of freedom? So you can see the formula over here. We'll screenshot it. Some micros. So there we go. 60 degrees of freedom. Great job, Noel. And there's the formula down here. The n minus 1 right there. The n minus 1. So So all you do is just subtract 1 on it, and those are the degrees of freedom. So n minus 1 is the degrees of freedom. So what does that tell you, Noel? It tells you the shape of the distribution. So you can see it becomes flatter. It's hard to tell on this one. I do love this applet. Huge shout out to Adam Spanbauer who made this. And so if you go here and you go to statdistributions.com, in the stat distributions applet, you can see at lower degrees of freedom, it's more flattened out. And when the degrees of freedom go up, it becomes more like the normal. So the degrees of freedom tell you the shape of the T, and it becomes more normal with more degrees of freedom. And if you're making a 95% constant roll, you shade the area between, and then the T approaches 1.96 as you get more and more degrees of freedom. Up, I'm going lower, so it's going away from 1.96. So the T interval is an interval to estimate the true mean, and the true mean is mu, where we have the estimate y bar, which is the sample mean, the sample standard deviation s, the sample size n, and the T star is related to the percent confident we are, and the T distribution statistic found on the T with n minus 1 degrees of freedom. That's a lot to take in. I would say break this up into parts. Do you know what S is? It's sample standard deviation. Do you know what N is? It's sample size. If you should know what all these are and know how to find them in problems. So in this problem, you are creating a one sample T interval, and it can be anything other than 90, 95, 99, and it's for quantitative data. So we're going to put a new thing right here, jump work for this. So let's go right here and go 853 stat 201 one sample T jump work. Okay, so this is how to do the jump work for it. You go to analyze distribution, because we're doing a univariate variable, analyze distribution, and then you go over here to your quantitative variable, make sure it's blue, it needs to be quantitative, double click, and there it is right there. You have now picked a quantitative variable to analyze, and you click OK. And now you go to the top right arrow, you go to stack, and then you go to the second red arrow. Top right arrow has stack. Second red arrow, you go to histogram options and count axis. Don't add in the probabilities about this one. It can get pretty messy with a lot of bars. You just add in the count axis. I like to make this a little bit bigger right there, make it a little bit nicer. And then we're also going to add in the confidence interval right here by going over here and go to confidence and other. Confidence and other. So with confidence other, you can enter in another interval other than 90, 95, or 99. We're going to enter in 98. Please enter in what you want, not 90, not 95, not 99. Enter in something else. I've chosen 98 for now. Let's click OK. So here we need to know what we are seeing. What do we have here? So Noel, or anyone in the chat, and I owe you some points on that, Noel. Do you know what any of the notation is over here? Now, this is not a required part of the assignment. Do you know what any of the notation is over here? Do you know what any of this notation is over here? Some of it is just said for you. Well, think these are sample or summary statistics, which come from samples. So all these are statistics. Well, that, and good guess, that's not mu. Good guess, we'll take some points for that. Since it's a statistic, it's y bar. So that's not mu, because that is the sample mean from a sample size of 300. The one thing I don't like about jump is it should probably call this n down here, because n is sample size. This is the lower bound on a 90, so that's the lower interval, the lower bound on the interval. This is the upper bound on the interval, upper bound, lower bound. And then the standard error is the SE y bar, which is found by s over square root of n, s over square root of n. That's the equation for it. So it's not SE y bar times s over square root of n. The equation for standard error, SE y bar, the standard error of the sample mean, is s over square root of n. And then the standard deviation is s. So you could literally go right here and say s over square root of n is equal to square root of 300. And you could go here to 31.77. And you can divide this, and we will get the answer on the bottom of the screen. So we go right here, and we go 300 square root, and 31.77 divided by that, and there it is, 1.834. Does that make sense? So that standard error of the mean is s over square root of n. It's known as standard error of the mean. Like it is the formula. Yep. So you don't, a lot of people, and I've seen this multiple times, they say, is this SE times Y bar? No, it's abbreviation. Evan, good to see you there. We're doing the project, so say hey and ask questions if you got them. So we have SEY bar is the standard error of the mean. Standard error is just a thing we talk about, and it's standard error of the mean. So this is the SE part of it. And as Evan probably knows, standard error means uncertainty. We could do some 320 at the end. Yeah, I think we got some time. We'll try to fit that in. Good questions, Evan. So standard error, you probably know from your class, 320, means uncertainty in a quantity. So it's like the metric of uncertainty we have. And if you notice, this is about 1.8. If you times it by 2, that's 3.6. And look at this. 79 minus 3.6 is exactly this right here. So it's basically 2. We might be able to do some chapter 15. Is that, Lean? Good to see you there. We're going to try to finish the project. When is chapter 15 due? Because if it's due tonight, there's so many due dates, right? I got to check every time and see where things are due. Try to put some 15 in this video. Is chapter 15 due tonight? When is chapter 15 due? Ooh, it's due tonight. I need to do some videos. So yeah, here, let's finish. We'll try to do the project, try to finish it up. Chapter 15, chapter BS 320. Let's do some work. So now we need to know what we need screenshots of. This was a review of what the output means. You need to screenshot this over here, everything here. I'd take this in one screenshot, and now I'd take my confidence interval in one screenshot. So with this, let's look at what the project wants us to do here and make sure we can interpret this. So let's go to the project page. And here we are on the project page. And we go down here to the project. And here it is. Going down, down, down. Wait, there we go. Here we are, the one sample T. Pick a quantitative variable you're interested in analyzing. We did that. Attack. Create a histogram, making sure it has a count axis, is in horizontal layout, includes screenshot, including the visualization, summary statistics, and quantiles. We did that. If you notice right here, the visualization you want for that is going to be the histogram itself, the quantiles, and the summary statistics. That's what it's referring to right there. Provide an appropriate write-up and explain the shape, appropriate center for the distribution, and spread. Now here's the thing. Let's mark this in the video because I see a lot of mistakes on this. So remember shape, center, spread from earlier in the semester. Shape determines center and spread. So how does my data look? Mostly what? Maybe a tiny bit of this, but I'd say it's mostly this. My data looks mostly this. Mostly this. And I could even check it by going here and doing this. And I'd say, that looks pretty darn this. Because it follows the this. And Evan should know this. I'd say, yeah, that distribution looks mostly this. Even by my initial look at it, yeah, it looks maybe a little bit. Mostly normal. It's exactly and exactly normal. It looks mostly normal. It maybe has a little bit of right skew. If you really wanted to see the skewness of it, you can go to summary statistics, customize. These are all optional things. That's what I'm doing. If I do something fast, it's optional. You don't need to include it. So you can go to skewness under customized summary statistics. It's probably going to have a tiny bit of positive skew, and there it is right there. So it does have a tiny bit of positive skew. But since it's mostly normal, the proper center and proper spread will be what? Since it's mostly normal, the proper center and proper spread will be what? Since it's mostly normal, the proper center and proper spread will be what? Mine's mostly normal, doesn't have extreme outliers. Since it's mostly normal, the proper center and proper spread will be what? Well, center is one of two things, and spread is one of two things. Center is either mean or median. Spread is either the standard deviation or the IQR. I had to think for a moment. So what would be the proper center and spread respectively? And what's interesting is that in the output, correct, great job, Evan, right there, you're right. So the output even kind of shows it to you right here. If your data is mostly normal, you actually go with this, and here's your proper center and spread. If your data is more skewed in nature or has outliers, so if you would say it's more skewed with outliers, then here's your center, here's your spread. The discussion over here would be the average. I don't want to say too much, but it's, the average. That's how you describe what that is the average attack power of Pokemon, and the The typical distance from the mean, that's what standard deviation is about this. That's what standard deviation is. It's a kind of standard deviation from a mean. It's typical distance from the mean, that's what a standard deviation is. More normal data is the proper center and spread. And if you have more skewed data, the 50th percentile of attack is 75, and the spread of the middle 50% is 45, because that is the range of the middle 50%, the IQR. You can also compute by doing the summary statistics, have it compute the IQR for you, the range of the middle 50%. But here's the thing, you don't give all the summary statistics. You report the appropriate one. You might say something like the appropriate center and spread. Remember, watch these videos, take in what I'm saying, and remember, you're picking the appropriate center and spread based on the shape of your data. Would you say because your shape is mostly normal? Yes, but then you have to interpret them in full. So you don't just say the center is this, the spread is this. You would say, you know, the center is represented by, see, like right here, make sure your interpretations are more than just the mean is this or the median is this. So you don't want to just say that, you want to say what the average means. It's the average, the mean is the average, right? So it's talk about what that is. And which I kind of just did a moment ago. I don't want to say too many words, lest everyone copy what I say, but you don't want to say the median is this. Think about what the median is, the 50th percentile. Think about what the IQR is, or into the middle 50%. Don't just say the IQR is something. Interpretation should bring context and not just cite values. Does that make sense, Noel? Don't just quote the values and then pick the appropriate center and the appropriate spread and interpret those values to the reader. So now let's do the next one, the confidence interval. MuBot can help us out right here. Okay. Yep, yeah, don't just say the values, Evan. Braden, oh my gosh, I looked too quick. I saw A-E-N, and so I was like, Braden, Evan? So MuBot is going to help us with the confidence interval right here. And I think we might already have it from yesterday a little bit. Here we go. I am blank percent confident that the true blank is contained in the interval blank to blank. So with this, you need to make sure you're interpreting it. So exactly, say the context of it. Say the context of everything and how it's associated with the data, and give the full context. So what was I trying to analyze with my data? What is the context of this? Think about this output. What was I trying to analyze? What was I trying to analyze? I was trying to analyze the true mean attack power of Pokemon. Notice how everything here stays the same, and then you have to start to, well, yesterday I was analyzing the proportion of legendary Pokemon. Today is the true mean attack power of legendary, of just Pokemon. Because when I did my analysis, it was done by going here and saying analyze distribution attack. So that's the true mean attack. Yesterday we also did legendary Pokemon, and we were analyzing the proportion of non-legendary Pokemon. And why would I say proportion for legendary Pokemon and then mean for attack? So look at the difference. So it's a good question. Why would I say mean for attack, like the true mean attack power versus the true mean proportion of non-legendary Pokemon? Why would I switch my wording? Why would it be the true proportion of non-legendary Pokemon and the true mean of attack? Exactly, categorical versus quantitative. Great job, Noel, right there. And then you're seeing it. So you notice, when do you say the true proportion? Categorical. When do you say the true mean? Quantitative, because we're analyzing the mean for quantitative data. These are the small things that help you study for the test. And remember, when you're interpreting things, proportions are for categorical, 1 prop Z intervals, where means, Mr. T, mean if you're doing drugs, is for quantitative data. So when we analyze attack, we're analyzing the true mean of attack. Hence why you see things like in the output right here, mean for the sample mean. So my interpretation would be, I am 98% confident that the true mean of attack is contained in the interval. The true mean attack for all Pokemon is contained in the interval 74.7 to 83.3. 2 decimals at 74.72. Make sure you get the lower and the upper right there. I am 98% confident. There's the 98. I am 98% confident that the true mean of attack for legendary Pokemon. Nice job. Boom. Oh, and I keep saying legendary. This has nothing to do with legendary. That just jumped into my brain. Braden right there, 1,000 points. Braden has the perfect interpretation using the lower, the upper, the context, and also the percent confidence. Great practice right there. Notice how you have to pick the proportion means or difference in means, the last chapter or second to last chapter we'll do coming up there. So good job, Braden. That is how we interpret our intervals. So excellent work. Name and define the three conditions. Comment on whether your sample passes or fails each condition. Regardless of the outcome, assume that all conditions are met before you complete your analysis. So with this right here, what you're doing is you are remembering the conditions, and let me mark this, conditions for the interval. Conditions to chart. Stat tool 1 sample T, condition. The conditions for a interval are random, 10%, and what? What are the conditions? So if you're practicing, see if you know it, 1 sample T, the third condition is what? What is the third condition for a 1 sample T interval or 1 sample T test? 1 sample T interval or 1 sample T test have what as their third condition? Ah, no, and Isabel with 5,000 points. Isabel, you are correct. Isabel got everyone the points in the chat. And I want to point out what Isabel's showing is that it is nearly normal because it's quantitative. So take a screenshot of this right here because success failure is for categorical. Noel does point that out. But remember, we're doing a t-test, so we're down here under nearly normal. A lot of people say success failure, but that's for categorical, where there's at least 10 successes, at least 10 failures, which was the one proportion interval we did earlier. So we need to have evidence the distribution of means will be nearly normal. So that's for the t-test, whether it's 2 sample, chapter 17, or 1 sample, chapter 15. Does that make sense? We will talk about the nearly normal here right now. So what is the nearly normal state? And once again, listen in on this because this is one of the harder things for people to explain, and I sometimes fear the graders take off points where they shouldn't. The nearly normal is the idea that the distribution of the mean will be nearly normal, not the data itself. So my data only has a tiny bit of what skew, right or left. My data only has a tiny bit of what skew. My data only has positive skew, think to the positive side, only a tiny bit of right skew. It's basically normal, and I could pretty much argue that it's nearly normal because it only has a tiny bit of positive right skew, and for the most part, there's just 2 slightly high outliers. For the most part, I think my data, like, don't copy everything I say. I'm saying a little bit quickly, but think about how I'm talking about this. I'm talking about, I think it's basically normal. But here's the thing people forget. The central limit theorem applet. And we call the condition now the nearly normal condition, but you can remember how large enough n works. That if we have a skewed distribution and we take a sample of 25, we are analyzing not the distribution of single observations. Say it with me again, we're analyzing the distribution of means of sample size 25. And the distribution of means of sample size 25, when we start to build it up right here, will show a more normal and tighter distribution. This is the large enough n. So even though my distribution has a little bit of skew, not even as much skewed as that, the sample size I have of 300 is more than large enough so that the distribution of the means will be nearly normal. Does that make sense? Does anyone follow any of that logic right there? Like, the original distribution can be skewed. It can be skewed. But the distribution of the means due to large enough n central limit theorem, because large enough n states as n gets larger, then the distribution of means, which we see down here, because every blue dot down here is a mean of sample size 25. And good job, Jack, right there. So then what you see is I'm building up a distribution, right? It's doing the simulation multiple times. And then you can see that the distribution of means will be one that is more normal and tighter by a factor of square root of n on the decrease to standard error, which is down here. It says standard deviation, but it should be standard error of the means. No, it's standard deviation because it's truth. Standard deviation and standard error, the nuance on that is so small. So we definitely passed the third condition, which is nearly normal, which can be passed via large enough n, which incorporates the central limit theorem. Try to think through it, maybe chat GPT my words and say, explain this to me. Give my instructor tips. I'd love to someone put into chat GPT what I said and said, make this make sense to me and explain it to me. And then someone said, hey, Brian, here's a better way to explain it. Because this is one of the hardest things for people to grasp a lot of times. The idea that the distribution of the mean will be tighter and more normal, not the singular observations. And we have to pass for the distribution of the means and not the singular observations. It's only like a few points on the test, like 2. There's not a lot of questions on nearly normal on the test. Little confused when we say it's mostly normal. We were talking about the shape. For example, we have a graph that is looking normal, but it's way off to the side of the line. Is that still normal? I'd have to see it. But remember, your distribution might be not so normal, but we are analyzing the distribution of the mean. So your distribution doesn't have to be normal. And it could pass via large enough n. So you could have a skewed distribution, but since our sample size is 300 plus, it's going to be the distribution of the mean is going to be more normal. Does that make sense, Noel? So although my distribution is skewed, if we do the distribution of the mean, the central limit theorem states our n is large enough such that the distribution of the mean is nearly normal, not the singular observations. This probably took me like a year to understand. You guys only have like a month, so I'm sorry. There's some things that are easier in stats, like, oh, that makes sense. And then I hope seeing it, someone maybe sees that visualization is like, I get it. I don't know. There's interpret the interval. I think we've done everything here. Check the rubric. I think we've done everything. Yeah, and here's the thing. Don't fret over it too much because it is only like 2 points on the test, 2 to 4 points, I'd say. I've done like 30 minutes on it before, and then people are still confused. Maybe I'm just not that good of a teacher. No, Brayden. I tell you what, let's do the next thing right here and see if I can make more sense. I think it's hard because it's very theoretical. It's like playing a song versus telling everyone how the chord progressions in the song make, it's like the theory behind it. So I totally understand. Okay. Side-by-side box plots. Let's talk the theory on it. Side-by-side box plots are used when you have a categorical X and quantitative Y. Categorical X, quantitative Y. Also, take a screenshot of this if you don't have it. Even try to reproduce it. We don't do logistic regression, so I crossed it out. And we don't like ring charts. Don't like ring charts. Ring pops, not ring charts. So take a screenshot of this and use it, and you'll do well maybe on the test. Okay. So we are going to create a side-by-side box plot right here. Side-by-side box plots are the visualization of a categorical X and quantitative Y variable of interest. And side-by-side box plots, I'm putting in the notes. And jump work. Let's go do it. And I think we can include any of them. We need to have the 5-number summary in there, so make sure to include that. Here we go. And we go back to our jump data. Analyze. There's 2 ways to do it. Either way is fine. Let's go. I'm going to do it this way. I did it differently yesterday, but let's go to Graph Builder. Let's go and put legendary on the X. That's categorical. And also, you can drop legendary in color. It's a neat thing we don't often do. And then we can put attack right here. So once again, you put your categorical variable down here. You put your categorical variable in color. And then you go here and put attack on the y-axis. Might be able to do, I wouldn't do that. It's not bad, but I wouldn't do that. And now, last but not least, you click here. And last but not really least, you click on the box plots, and then you go to 5-number summary. There we go. And do not forget to click done. Do not forget to click done. If you don't resize the window, you can just resize the overall window and get it nice and pretty right there. You might go like this because we're putting in a Word document and give it a little stretch. Make sure the numbers are not overlapping. That can happen if you have way too many groups. I think you can also click these if you want and change the colors, which is kind of fun to do. But yeah, you could change to whatever you want. And sure, cool. Yeah. So whatever you want, however you want your graphic to look. If your dots are dimmed or bright, make sure to click to something else. You just click on the graphic. A lot of people have selected some dots, which dim it. Click away and choose right there. So that is how you make your side-by-side box plots to compare the attack power of legendary versus non-legendary Pokemon. So cat is on the bottom and quant is on the side. Just checking you are correct and it should look like this. If it doesn't look like this, something happened. So let me see. Now, what do you immediately notice about legendary versus non-legendary Pokemon? I mean, there's an immediate thing right here. You want to compare and contrast. So mine are pretty darn obvious. So we want to compare and contrast. There's, I'd say at least 3 things I see off the bat like this. three things that are pretty darn obvious. Nice, good screenshot. Anything? Bueller. What do you think? I would say immediately this. The 50th percentile of legendary versus the 50th percentile of non-legendary, there's a difference of 34, where legendary Pokemon have 104 versus non-legendary have 70. Notice how I'm quoting the numbers as I just talked to you about this. That's what you would be writing. You'd mention the difference, that there's a huge difference where it's like 30 more, it's almost 50% more, because 70, half of 70 is 35, so it's a big difference. Legendary Pokemon have a much higher attack for the 50th percentile, not on average. No dog, just the bunny. Just Morty. He's over here still sleeping. Good bunny. And then we got Jolly here, I think. This is Morty Bunny. Just Jolly Bunny. You get a little bunny break in there randomly. So also we see here a difference in mins. The difference in mins show that even the minimum, and if you look, the minimum of legendary is close to the 25th percentile of non-legendary, where the minimum for legendary is 50 and the minimum for non-legendary is 10, probably like a Shuckle or something, like a little Blissey Pokemon or something, I don't know. Pidgey, go Pidgey, Magikarp. And the 25th percentile of non-legendary Pokemon is 55. So clearly even the weakest of legendary Pokemon they're better than about 25%, because this is where the 25th percentile would be. 25% of non-legendary Pokemon have attack at this or below. So clearly even the weakest of non-legendary Pokemon are about as good as the bottom, at least the bottom 25% of non-legendary Pokemon. There are outliers, so it is worth pointing out that there are very strong legendary and non-legendary Pokemons, and what's interesting also to me is that the strongest Pokemon for attack is a non-legendary Pokemon. Tyranitar's not legendary, I don't think. I'm probably way off on my guesses, I don't know. I only know to Gen like 5, and then I just get lost in Pokemon that are keys, and I mean, I guess we had Egg Pokemon in Gen 1, so why not make key Pokemon? So, right, now we got garbage Pokemon. Well, I guess we had mock Pokemon. So Pokemon have always been weird, Brian. And then that's a similarity, I would say. And then another similarity is the IQRs, which is the range in the middle 50%. In this one, it is 40, and for this one, it is a not fun number to calculate. That's going to be, so that's almost 30, and it's 8 off of it. Oh my gosh, my brain needs to speed up. So it is, I think, 29.8. Let's find out. I think it's 29.8. Q3 minus Q1. 28.8. Wow. Doesn't matter where the outliers are. Like if for true you have outliers, you just interpret it. The outlier is going to be where the outlier is going to be, and you're going to just explain the differences in what you see. Your data is going to look like your data is going to look. You want to compare these numbers. Talk about what you find interesting or not interesting. If I was doing in-depth research on this, which it's not actually hard to do, what's really cool about Jump is you can go back here and you can just go to this data point and highlight it, and then go to tables, subset to find it, and it's Heracross. Heracross Mega, so it's a Mega Pokemon. So that kind of makes sense. So the strongest, so I could even mention that, like in my report. Like if I wanted to go more in depth, you don't have to go that in depth. The point is, you know what these values are, and you can compare and contrast the distributions of you can compare and contrast the quantitative distributions between two levels of a categorical variable. That's what I wanted to say. So think this is the quantitative distributions of two levels or more of a categorical variable. Does that make sense, Noel? The point is, can you make these comparisons? Can you compare the mins, the medians, the Q1s, the Q3s, the IQRs? Can you talk about similarities and differences and explain to the reader what's going on? So include right describing the association. So the association seems to be, in general, legendary Pokemon have higher attacks, but there are things that break that trend. The Heracross Mega breaks the trend. Provided my evidence. How similar are these and how different? So I do like this one. It's pretty short. It's only 10 points, but that's got it. Now we're on to regression. Whew. Let's talk regression theory first. And great work, Noel. We are almost done with the project. So when do you use regression? When you first learned regression, I taught you QQ straight enough, no outliers, plot doesn't thicken. You bet, Evan. We'll definitely look at that. Prof, look at it after hours, but you're right. QQ straight enough, no outliers, plot doesn't thicken. What in the world does that even mean? Well, to do regression, you have to have two quantitative variables, unless you're doing logistic regression, right, Evan? Unless you're doing logistic, categorical Y, quantitative X, but we're only doing regression right here with quantitative, linear regression. So to do linear regression, you need quantitative. I think this makes more sense to Evan now, especially being in 320, that logistic regression can be done for a categorical Y versus scatter plots are for quantitative relationships. And so we go here to fit Y by X because a regression is bivariate. We also call it simple regression if we're only having one X, one Y. Multiple regression has multiple X's and one Y, and you would do that under fit model in JUMP to do a multiple regression. And you can just dump in a bunch of X's now and get what is called a multiple regression right here with p-values for the significance of all the X's versus individual X's, and then a p-value for the significance of the model found under the analysis of variance section. Also, a goodness of fit test was done on the model to see if the model has a good fit. It looks like it didn't run it, yet somehow it was not able to produce a lack of fit test, which is a test to see if we have linear fit to the model, similar to the check regression in 320. All that for 201, you might be saying, what in the world? That's where we go with more advanced models. You're just doing 1x, 1y. So all you want to do, let's put this section right here to the JUMP theory, or the JUMP creation. We are going to create our model now. Stat 201, regression, JMP work. Okay. So this is how to do the regression in JUMP is to go here to analyze, fit Y by X. 1Y, 1X, simple linear regression. Both variables are going to be quantitative because we're doing linear regression. And we will put in a tack that I'm interested in with defense. So we are seeing, does defense explain why attack is so high or low? We don't know the relationship yet. I might think that it's positive that Pokemon that have higher defense generally have higher attack, and here's the relationship. I was right. But we do have a bit of outliers, especially this one right here. Let's first fit the line to the data, which is the idea of regressing Y by X. So we go here to the red arrow, and we go to fit line. I do want to say, though, and I love saying extra things, if you wanted to add in the naive model, if Evan's still watching, you could go to fit mean and get the naive model. The naive model is the mean of the Y variable, and you can see it right there, the mean of the Y variable, which is the naive model, when we don't need that. Yay! Yeah, sir. Yeah, and Evan's got it on there. So Google White Pages is basically, yeah, and Evan, do you want to drop some notes on that? Evan literally dropped in the chat. Evan and Caitlin, let me throw you some points. It's how we're going to do our format, and it's how you're going to turn your report that everyone's going to read next Monday. And so with that, it's basically, and Evan's posted it, it's basically, it's going to look like a very boring report, and then we're going to sit there and read it, and the graphics are going to be at the end of the report. And Evan's got some really good format on it and had some really great advice. Thank you, Evan. And we'll answer some more questions on that. And Evan might even know it better than me. And it's so fortuitous that you ask her while Evan's here. But Evan has a lot of experience with it. And also Dr. Michelle Ballings was the one who cued it into my attention. So thank you, everybody right there. Really good questions. And so with this, we have our regression model right here, which we've been doing a lot of this in 320. And you can see all the output, the lack of fit, which we do in 320. There is not barely evidence of a lack of fit. Thank you, Evan. Good comments. And here we are with what we need. I'm going to make the output a little nicer by bringing this to 2 decimals. And you can make this pretty right here. Defense is going to be that. And this is going to be down to 3 decimals. That's rounded to that. These same coefficients can be found down here at the bottom. And this is what I would include in my screenshots. I would include everything here and also the residual plot. To get the residual plot, go here, the red arrow under linear fit, and go to plot residuals. You don't need all of these residual plots. You only need the first residual plot found right there. So we got a lot of things open. We got the residual plot down at the bottom. I'd probably do this in multiple screenshots, but you might be able to. I wonder. You click here on this and click and drag. I like it. Now what I'm going to do, see if anyone does the report like this. you have to click on this. This allows you to drag and drop things. You click it one time and then you drag and drop. And if you saw it brought that little arrow over there, it has to be over there. I'm going to get a double click of it. So the reason I like this is I can now go and screenshot this. And I have my regression output and the residual output side by side. And I got it to where it's sized nice and neat. I'm not getting that extra stuff. If you look at how this looks in a Word document, you could just do them individually if you wanted. But there is the regression and there is the residual plot. And it's even more clear to you if you look at this, that the residual plot is just the line flat. Look at that dot there. Look at these outliers over here that are far away. It's clear to see that that's the highest outlier. We don't really have many low outliers. And there's a little bit of maybe plot thickening. Here we'll do plot thickening in a different color. Maybe it gets thicker. Here we'll go back. There we go. And it's easier to see this in the residual plot versus over here. It's the same sort of idea, but I think it's easier to see in the residual plot. Thank you, Evan. Good comments. And so with this right here, the residual plot just lets you see the value of all your residuals. This Pokemon's attack is, wow, and that's crazy. It's like 120 higher than we would have expected. The model is not close to predicting it accurately. Once again, we can find out which Pokemon this is that has a way higher attack than we would have thought, and you can't highlight it there. Go to table subset, no, table subset. Once you highlight the point, these are not required, but it's fun to do, and that is Deoxys attack form. Well, that makes sense. It's the attack form of Deoxys. So you can find out which points these are, and you can give a screenshot of your scatter plot with the line on it, and also your residual plot right there, which is the line flat, letting you see what's above and below the line. Finally, you need a screenshot over here of all this output. Let's review what the output is again. Regression output is as follows, and this will help with 320 also, because this is what R looks like. What you have right here is y hat equals b0 plus b1x, and then you have r squared, which is the percent of variation in y explained by the variation in x. Thank you. Yep, we're just going Amazon on this last one. R squared adjusted is the percent of variation in y when we fairly critique with how many variables in the model, not included in stat tool 1. Root mean square error is the typical miss the model makes, not included in stat tool 1. Mean of the response is actually y bar, which is in stat tool 1, but we won't interpret this right here. It's like 2 monster types a day and finish the project. Oh, I should get a 2 monster a day. And then observations is sample size n. Down here, the intercept, I'll have to put these above them or so. We'll put them right below. The intercept estimate is B0. The slope estimate is B1. This is the name of the X variable. The standard error is going to be the standard error, which is uncertainty in B0, standard error of B1. The T ratio is the estimate divided by the standard error. So you can literally just take 47 divided by 4 and get 11 something. And then the p-value of the slope is the significance of the model, which this is super duper significant because the p-value is close to 0. So actually what we just did looking at this jump output, there's things in tool 1 we won't use. So we won't use standard errors for these values. We will use those in 320. And everything else that I don't have x's over, you need to understand. Because what is r squared? R squared is the percent of variation in y explained by the variation in x. The mean of the y variable right there, the sample size, 300 were taken. I'll just remove things that notice we don't need them on. We don't need to do t ratios for this. It is t because it's quantitative. And there's the estimates down there, which are up top. So how would I interpret this? Let's talk about slope and intercept in r squared interpretation. Mubot will have them here in the chat. And slope, intercept, and r squared interpretations. Let's put these in the video. And interpretations. So to interpret the values of the slope, the intercept, and the r squared. Give us the lecture. Yes, you got it, Kaylin, right there. I will. Let me post that right away after this. Thank you for asking. So with the value of the slope, first identify it. The value of the slope is known as B1. And that helps remembering it because you think with B1, It's for each 1 unit increase in X. In notation, it's B1. So what is X? It's defense. So for each additional unit of defense, we'd expect a Pokemon's attack to be higher by 0.415. Now be careful, we don't want to say it will increase. Not that for each additional unit of defense, the Pokemon's attack increases by this. It's just what we expect, or the model would expect. And you could also say, I'm a little afraid because my set to 1 graders, maybe don't say this, but 2 Pokemon that differ by 1 unit of defense are expected to differ by 0.41 units of attack. Not that it will, not that increase. So Evan, make sure, and for 320, remember, it's that we would say that 2 Pokemon that differ by 1 unit of defense, we'd expect their attack to differ by 0.415 units. So we expect when we see these differences right here, so very important for 320. And with the intercept, yes, differ by. And then 201 interpretation says, you have right there, for each 1 unit increase in defense, we expect the attack to be higher by this. We expect it to be higher by this on average, like that little on average. No worries, and good job, Evan. Good practice in the chat. The intercept is probably illogical because I don't think a Pokemon can have defense of 0. When defense is equal to 0, when X is equal to 0, we expect Y to equal B0 on average. So let's highlight the coefficient of the intercept. When defense of a Pokemon is equal to 0, we expect its attack to equal 47.58 on average. That's probably illogical because a Pokemon can't have defense of 0. Not even Shuckle or Blissey has that. Last but not least, we have R squared. R squared is the percent of variation in Y explained by the variation in X. So it would be 18.6, make sure to times by 100, so 18.7 if we round properly. 18.7% of the variation in attack is explained by the variation in defense. So very important right there. 18.7% of the variation in attack is explained by the variation in defense. So with this right here, I think that did, let me check the notes. And we got the residual plot, and we need to look at the conditions. So I kind of went over it. Name and identify the 4 conditions. So let's put in here the 4 conditions, because I didn't go over that explicitly yet. Stat tool 1, regression, the 4 conditions. Okay. Do not write heteroscedastic, homoscedastic, independence, time ordered. No. QQ straight enough, no outliers, plot doesn't thicken. QQ straight enough, no outliers, plot doesn't thicken. So when you get your output here, what does QQ mean? Well, say it in its full form, 2 quantitative variables. That's why I say QQ, 2 quantitative variables. Well, obviously, because we're making a scatter plot. Don't write down exactly what I say, but think. A scatter plot requires 2 quantitative variables, so I got a scatter plot, so I got 2 quantitative variables. Don't write that down. Think about it. If you have it, you pass it. Yes, Braden knows right there, 5,000 points, Braden. Yes, so we have 2 quantitative variables. Straight enough. Does the straight line well approximate the relationship? And if something passes straight enough, it's going to be that when you draw, the points are generally around the line like that. This would not pass straight enough if it bends. If the points are bending around the line, then it'll still fit a line, just won't be straight enough. So you have to look and think, do my points generally follow a linear pattern? I would say mine do. I'd say, yeah, for the most part. No outliers. Literally, this means, are there no outliers? And I have outliers. You might even go here and highlight a point, go to rows, under rows, go to color. You can color a nice light purple, and then go here and go to rows again and go to markers. This is not required. It just highlights your big outlier. And if we had done this earlier, we copied this, we could then have the residual plot copied over there, and we could see it up there as the big outlier. So once again, not required, but I've got outliers. So I don't pass, bit of a problem with the outliers. And then the last condition was the plot doesn't thicken. And we can look at the residual plot right here, and we see we do have evidence of slight plot thickening. I would say it's really not super duper bad because there's a lack of data, but for 201 standards, a bit of a problem. and the plot gets stronger towards the end. And actually, there is a small evidence of nonlinearity towards the end because the center of the data is down here if you average the points. So yeah, it's like going really in depth. I didn't see it till that moment, but if you notice, if you average those points. But once again, if you say it's mostly, we want to look for big problems here. Did it pass the lack of fit? It did pass the lack of fit. That's not a 201. Visually, it's mostly good. Small plot getting thinner at the end. Don't like that. Small dip below the line. You see how it dips down here at the end below that line, which is that line. That's small nonlinearity. So I'm starting to notice things the more I look at it. And here's what we say, especially in upper level stats. If you have to look at it a whole bunch to find problems, probably not that big of a problems. So I think there's minor problems with no outliers. We've got a high outlier. I think there's minor problems with nonlinearity. At the end, it slightly dips below, indicating a nonlinear trend. I think there's minor problems. Exactly right, Evan. And minor problems with plot doesn't thicken at the end. It gets a little bit thinner, but there's lack of data at the end. So lack of data means lack of spread. So you're not meant to go in that depth. You're meant to know what the conditions are and meant to know how to kind of visually check them. We'll go into more in depth in later classes, but know what QQ straight enough, no outliers, plot doesn't thicken is. Do you write up? Mewtwo told me to not let you forget, but if you have a chance, can you look at my, yes. Double message, make sure to message me on Discord, and I will today look at the code because I want to look at that and see what's going on with it. We're almost done with the project right here. I figure we'll put this in the full video. We did the 4 conditions, we did the interpretations, also evaluate if your regression model is statistically significant. So I'll put it right here. It's in your DMs. Thank you so much, Evan. Check your DMs. Statistical significance. For statistical significance, you need to look at the p-value of the slope, which is right there. The p-value of the slope will indicate something is statistically significant when the p-value is below 0.05, which means the relationship we are seeing between attack and defense is unlikely, low p-value, by random chance. So we have a statistically significant relationship here because the p-value of the slope, not the intercept, the slope down here is very small. If you hover over it, you got to click and hover. It's super duper small, 4.27 e to the negative 15, which is like 0.000000000000427. Crazy small p-value, super duper significant. And I think that's got it. Here we are. Let's finish off right here with the executive summary. What does it mean when Jump shows the p-value in red? Good question. So actually, this is what we get in R also. Jump color codes p-values. The more significant they are, the different the color. So if you notice right here, this p-value is not significant. It's a p-value for an F test for lack of fit. Did not come back significant, does not get a star, and is not colored in red. So Jump uses color coding and stars to denote statistical significance. Good question, Noel. 5,000 points. So when something is statistically significant, it gets the color coding and it gets a star to denote statistical significance. Versus this p-value right here, prob greater than f, is because p-values are probabilities, the p of p-value. It is not statistically significant because it's greater than 0.05 by the alpha 0.05 standard and does not get colored in red and does not get the star. Good question. Executive summary. So let's talk over the executive summary now that we're done with the report. Can you repeat it again? It's statistically significant if it's less than 0.05, less than alpha. P-value less than alpha, statistically significant. Great job, Braden. Noel, more points. Greater than or equal to alpha, which is generally 0.05, not significant. Statistically significant means unlikely by random chance, low probability. So the executive summary. The executive summary is the introduction to the report, but also it's the full report. Your executive summary needs to have 3 parts to it. Don't include the prompt. So you need to have some, first of all, you're going to introduce the reader, which is kind of the introduction. Like, I'm writing this report for Nintendo of America. I've been working there for 3 years, and we're trying to analyze the relationships between attack power and other variables along with legendary Pokemon. So I did my report, right? Don't copy what I say. Don't say I'm writing this report for such and such. We're trying to analyze. Don't do that. Just sit back and enjoy and think about what I'm saying, but don't copy what I say. And now I'd have to go through and write my key findings. Key findings were the percentage of legendary Pokemon were found to be this percent versus non-legendary this percent. We also analyzed attack and found key differences between the attack power of legendary and non-legendary Pokemon, where medians differed by this much. Insert the numbers. I can't state this enough that you need numeric backing, and that's usually where students lose points. So you need to include numeric backing. This is about maybe a little longer than this. That's about how long an executive summary should look if you look at the size of it. So first part, you're introducing the reader to what the report's about and what you're going to analyze. Second part, you're giving the key findings with numeric backing. And last but not least, you're going to give an action item. I would say we think here at Pokemon of America that we need to be introducing more Pokemon that are legendary that have a higher attack than the non-legendary Pokemon. Because why is it that Mega Heracross is going to have the best attack of all Pokemon? So next generation will have a Pokemon with the highest attack power released of all Pokemon ever. And in addition, we might have a Pokemon that breaks the trend on its attack and defense, because we do have Deoxys that breaks the trend up here. So why not make a Pokemon that has crazy high defense but no high attack? Like Blissey gets what if there's a legendary evolution? Blissey gets a legendary evolution. It can evolve into a legendary Pokemon, which we've never seen before. Non-legendary Pokemon becoming legendary. We're going to do something crazy that never even talked about, but it'll be legendary Blissey with like steel attack or steel defense. It's going to have no attack. So you just come up with what you want. So we have to write these prompts. We have these prompts to write, but we don't also include such stuff. Oh, no, you do include the screenshots. Not in the executive summary, though. The executive summary is just the opening. It's kind of the white paper of the report. The executive summary is your elevator. Like you go into the elevator and someone says, tell me about the full report. And you tell them everything. You tell them what it was written about. You tell them your key findings, and you tell them what you're going to do. And Evan said you're going to have your images in the report. So the executive summary is the start of the report, kind of like the white papers, where you literally just give the full report. The point of the executive summary, I wish I had a piece of paper right here, is that someone could take the executive summary and just read it and know your report. So your executive summary should be your full report. I know that's crazy. It should be who's the report written for, why you're writing it, and what'd you find in the report, and what are you going to do? So you saw me and you heard me say, I'm going to introduce a legendary Pokemon that has the highest attack. Also, we're going to introduce a legendary Blissey that has something that breaks the mold on attack defense, where it has crazy high defense, low attack, and it's going to be an evolution to get people excited as the transition from non-legendary to legendary Blissey. It'll be called Blissa Pokemon. I don't know. We're gonna workshop the name. I'll put that in the workshop name. So last but not least, you have the future research. So future research right here. What is future research? Future research goes beyond the report. Future research is things you have not covered. Give ideas for future research. It's all right to briefly mention what was covered in the report, but don't use this section to mainly go through results you've already found. Your goal in this section is to talk about research that could be done in the future. So I think we need to analyze these newly released Pokemon as they're coming out and look at trends on social media. What are people saying? Are people using them in the card games? Are people excited about them? Is there buzz, like Beedrill or something buzz? Is there buzz about the... I'm getting lame jokes these days. Is there buzz about the new Pokemon? Are people excited? Have we made good choices? What's the analysis after they're created? We need to track this and we need to analyze this in real time. And then we'd be like, ha, we could release them on April Fools. And then we could be like, ha, it's a joke, guys. We're not doing these bad ideas. This is the collection of data we need to do from here. This section covers the data that could be on the report. So we don't have the data on how the new Pokemon are received yet. We don't know how they'll be received, but we'll analyze how they'll be received and we'll deliver you the next report next time on Stat 201. So with that, it is almost time for class right here. So I'd like to thank everybody. Where is it? Let's head back to the main screen. Oh no, wait, let's head back to this screen. There we go. I wanted that right there. Maybe I'll leave that for class today. I think it'll take over. Did you say I needed to send you a follow-up? No, as long as you sent me one thing on Discord, I'll check it out. I wanted to put the full everything into this video. One message is good. Yeah, I should be able to check it out. My goal with this video, and I might need to come back and do a stream for homework 15 today because there's a lot of work. Projects isn't due till Friday, but the video's out here and I've put tons of sections in this video. Like everything is covered, broken down into little bite-sized sections. Just I know a lot of people need help with the project, so I kind of dedicated this. And tomorrow we'll probably I probably won't do much project. So Evan, especially tomorrow, and thank you Evan and everyone else. So yeah, so I tried to go as in depth as I could, tried to break it down to each part so that anyone comes back to this, they know exactly what's being covered and when. So you can see clearly everything. And I was like, I'm just gonna dedicate this whole video to this. But you're welcome, Braden. So yeah, check it out. The other video too. We have it linked, or was linked to start. I'll pin it again. But the other video, also sent out as an announcement, has everything you would need to. It's all labeled. So it's all labeled right there. Introduction to Statistics, MIT open course. I want to find that, and that's not, let me go look at it. I'm gonna get in trouble if I play this video too long. Part 2. Don't copyright claim me, I'm just looking at your video. What are you covering? Probability. Sure. Fun. 7 years ago, is it? 7 years ago. What are they teaching? Is it just he's like, what this course will cover and what it won't cover? That's not telling you that much. Talking about research. Let P denote the proportion of couples that turn their head to the right when kissing. Let's design a statistical experiment and analyze its outcomes, observing N kissing couples times and collect the value of each outcome. And then he's doing a binary operator for right, left. And notice right here, thank you. Oh, thank you. MIT's pretty awesome. I know a really cool professor at MIT. I appreciate that though. And there's P hat. He doesn't even show you the formula. What are you doing? Thank you, Didi, in the chat. No, this, I mean, it looks pretty good. It's like, why are you doing this? Why are you analyzing this? Well, at this point, you know what's cool? Here's how easy it is to analyze. 80, 124. So watch this. Actually, we could do it in jump, but it's way easier in R. So I'm opening up R right here. The numbers were 80 and 124. Oh, that's a good channel. Didi's got good advice on channels right there. Didi, if you want to drop that link in the chat, number file. Really good channel on cool things with data and mysteries with data. They are an excellent channel. So watch this. Prop test. No, not prop table. Prop test. And then 80, 124. No. And there's the analysis. And we have evidence to reject the null. Thank you, Didi, right there, number file. So it's really good. Really amazing channel too. Like I think they're better. I think this is, I bet you this MIT course, it's just not really, the way they recorded it is not the best for online. Like it's good. It's a good classroom recording, but hey, I mean, it's MIT and he looks like a good presenter too. So, but online structure is a little bit different than like the way you present things. I mean, who am I to talk? They're getting the 2 million groups. But the analysis right here would be that there is evidence of a difference, because especially look at your confidence interval. If you're comparing the truth is 50%, you could reject 50% and have evidence right here. So there'd be evidence of a difference. Does he get into that? Oh my gosh, stop. Don't want to play too much and get in trouble with the copyright claim. Now he's talking about an accurate estimator. Don't copyright claim me, guy. Seem like a nice guy. Go check out this course if you want, or I'll drop your link. So we're not stealing content, we're just checking it out. Now he's talking about, comes from a distribution of 0-1, Bernoulli trials, fun stuff. This is, okay, he's teaching at a much higher level than I'm teaching it. And then he's making an estimate of what the truth would be. Yeah, it's, he's doing it at a much higher mathematical level. We're kind of blended between business analytics and statistics. Full course. What's she teach? Okay. Don't get mad at me late. Okay. That guy and that lady, just don't get mad at me. Check all these arguments. Is there a main effect of drug type on the blood reduction in blood pressure? Okay, so they've got, looks like a study they're doing with drug and gender, and they're trying to figure out the reduction, and they're trying to figure out if the drug is doing it or maybe gender is doing it, and then they'd look at the effects right here. So they would have to look at the effect, and so it looks pretty good. She's looking at the sums of squares total right there, which is the sum of the sum of the sum of the, man, even I'm of the mean of G bar. I think we use X bar, Y bar. Y bar is the mean of the Y variable. G bar is what they're analyzing here, I believe. And yeah, it's what they're doing is they're finding the difference. That's a sum of square. So you notice it's square, and they're summing it 3 times. I don't know what sum of. I think that was like AI done or something 6 months ago. So I could be an AI telling them it's. I just don't understand why it's sum of. The sum of squares total. The total error in the model. Sum of squares error. So the sum of squares total is how much you miss by from the naive. So yeah, because G bar is the mean of the model. Oh man, I'm just sum of square error is how much the model misses by. So the predictions. So for the IJ individual, oh man, it's making me think. Wait, the mean of the AB individual? Normal distribution. I'm just having fun looking at data. They do these at such high levels. Like, I'm like, if I'm having to think through this, just looking at, I'm sure she explains it, talking about sums of squares, but it's at a very high level. I'd love to know anyone who watched, of the 500,000 people who watched this, how many people retain it? It's a problem we run into. Please don't copyright claim me. Oh, wait. Is this Shapiro W? No, it's not Shapiro W. No way. I'm gonna actually have to go watch this. Shapiro? Yeah! It's Wilcox and sign rank. I thought it was Shapiro W. No, it's Wilcox and sign rank, which is a way to test differences. Yeah, it's Man Whitney U. Tide rank. All right, fun stuff. Okay, I think I lost everybody. And hopefully I just didn't get copyright claims on the channel. But man, there's so many stats and so many things to remember, and it helps jog my memory. With that, full video done, going through the project. Well, thank you. Yeah, I see it, and I'm like, how much of this do I remember? And a lot of things are covered here for you guys. A lot of these topics we talk about and we go into in depth on, and like she's doing other correlations right here. Pearson and Kendall rank correlation. There's Spearman rank correlation, Kendall rank correlation, and Pearson correlation is Pearson's R. But with that, I bet it looks like a good video. Looks like I explained it really well. Like a lot of topics, I might watch it and just have it on the background, just hear it and learn things, because you have to know things to know things. So hopefully it would help me in my knowledge. With that, bye for now, everyone. Bye.